Yes, sir, start.
So are you ready?
Yes, sir.
Okay. So I'm starting. So today's experiment is again another experiment on determination of thermal conductivity. Sorry. There are so today's experiment is measurement of thermal conductivity of a metal rod. Can you see the screen?
Yes, sir.
Okay.
Yes, sir.
Okay. So here, because it's the metal rod, so here the method will be much different. Okay. So the objective of the metal experiment is to determine the thermal conductivity of the metal rod as a function of temperature and to study the temperature distribution along the length of a metal rod. Actually, the objectives are given in the way in the sequence of their importance, but if you think of the sequence of the of execution, then it should be the other way around. That means first we shall study the uh, first we shall determine the temperature distribution along the length of the metal rod and then use it and some other information to determine the thermal conductivity as a function of temperature. Okay, so let us see how it is done. So this is the schematic diagram. Here we have a metal rod which is heated at one end by an electric heater and cooled at the other end by a cooling water jacket. Okay, and on the side we are there can be heat loss at the side, but the heat loss from the side is reduced, not eliminated, by putting an insulation of asbestos, a coaxial cylindrical uh, structure of asbestos. And on the rod itself there are 9 locations at which the thermocouples are placed to measure the temperature. So 9 equally spaced locations from where we can get the temperature which gives us the temperature profile of the profile in the metal rod. Okay. So if you think what is happening here, so here there is a hot end and there is continuous heat loss from the sides, though the heat loss is reduced significantly by the presence of the insulation, and then finally there is some heat loss from the end also by means of the cooling water jacket. So the situation is very much like a fin with convective tip heat transfer. Okay, you have studied that, right?
Yes, sir.
Yes, sir.
Only difference here is that in case of a fin, classically in a fin problem, we normally specify the base temperature, but here we know how much power is supplied, not the base temperature. At different locations, we measure the temperature. Of course, we can take this first thermocouple location as the base of the fin because it is very close to the heater. Okay. Apart from that, we also put thermocouples at 4 locations inside the insulation. 4 locations inside the insulation. Why? Because by studying the temperature difference between this T10 and T11, for example, or T12 and T13, we will try to estimate the radial heat loss. That means the heat loss from the side of the rod. Okay. So of course, this will involve some amount of approximation. We will discuss about it, but these are the measurements. So basically here what you have to measure, basically in this experiment, measurements are primarily some temperature measurements. At least the measurements that you will use in calculations are mostly the temperature measurements. So 9 temperatures along the length of the rod, 4 in the insulation, which makes it 13, plus 2 temperatures measuring the inlet and exit temperature of the cooling water. So if we know how much, if we know the mass flow rate of the water, of the cooling water and the temperature and its temperature rise, then we can find out how much heat is lost from the fin T. Okay, so these are the 15 temperatures that we measure. So how does the setup look like? This is how it looks like. This is basically the rod. One end of it is, at one end of it there is the electric heater. So to prevent heat loss from that end, it is put, there are some insulating tapes are put on here. At the other end, this is the cooling water inlet. So this thing is the cooling water jacket, and this is the inlet pipe, and this is the outlet pipe of the cooling water. Okay. And this big cylinder, this is the insulation, which is this cylindrical region is filled with asbestos, so that we get a very good insulation. Like the insulation that we had seen in the other thermal conductivity experiment. Okay. And and this is the control panel. So this is again the main switch where we are measuring the, where we are supplying the power, and this is the heater control. Again, the thermostat control, which is basically given in watts, but as in the previous 2 experiments, this is mainly for the purpose of setting, not directly, these values are not directly used in the measurement. Okay. So basically, this is to ensure repeatability of the results. So this is to change the setting. How do we know that we have significantly changed from one condition to the other? For that purpose only. The actual power input that is coming through this voltmeter and the ammeter. But here you will see that unlike the previous 2 experiments, here we do not even measure the power input through the input to the rod. That is, we do not make use of the voltmeter and the ammeter calculations, but we take the readings. We can, if we want, we can do a kind of energy balance. Okay. And this is the temperature indicator. But now you can see that there are 15 points at which the temperature has to be measured and whose values have to be noted. So we need a temperature selector switch. So this is the temperature selector switch. So in an initial design, it was like this. There was a toggle. By putting it on one side, it was you could get the readings for for 1 to 12, and putting it on the other side you could get it for 13 to 15, but now it has been replaced by a 16 a 16 port kind of thing, a selector switch, 16 plus selector switch, where we can, by choosing the selector switch appropriately, we can get the appropriate temperature. I mean, this is exactly similar to what you had done for the other two experiments also. So more closely the first experiment, where with the indicator switch you had measured 10 different temperatures. Here you can measure 15 different temperatures. There are provision for 16 temperatures. Selecting the temperature selector can choose 16 different temperatures, but here we have connections for 15 of them. Okay, so is this part clear?
Yes, sir.
Okay.
Yes, sir.
So this is the specification. Basically, let me show you the. Okay, so here what are the things given? Length of the metal bar, that is 445 millimeters. That means the length from this end to this end, the full length. But the test length of the bar, that means over which we are putting the 9 thermocouples and measuring, that is 176 millimeters. That is this portion only. This is 176 millimeters. But there are the remaining part of it is inside the heater, and part of it is inside the cooling water jacket. Okay, and the diameter of the rod is 25 millimeter. As I said, there are 15 positions of thermocouples, 9 on the metal bar, 2 in the insulation shell, and 2 in the to measure the rise in cooling water temperature, and they are all of chromel alumel type. That is because they are not measuring very high temperatures. I told you in the last class that there are different types of thermocouples, and basically denoting the combination of materials, combination of the wire materials used in making the thermocouple joint. And most of the times it is and depending on the temperature range, you have to choose those materials, because different materials will give will generate maximum voltage at different temperatures. Okay, and the heater coil is again a nichrome heater. The cooling water jacket diameter is 90 millimeter. That means this diameter is 90 millimeters. So this is even bigger than 90 millimeter. And then there is a digital ammeter and the digital voltmeter. And there is a thermostat for the heating coil, which is 230 volt AC and 2 ampere, 230 volt AC and 2 ampere as the ratings. And then there is because we have to have measure the flow rate of the cooling water, so we have to have a flask for measuring the flow rate, a graduated flask for measuring the flow rate, and a stopwatch for measuring. A flask and a stopwatch for measuring the flow rate. In a given time, you will collect the water for a given period of time, and then the graduated flask will tell you how much volume of water has been collected. So that's how you know the volume flow rate of water. From which you can get the mass flow rate of water. Okay, so now what is the principle? So basically, first you consider we consider 3 sections. This section A, which coincides with the location of T9, that means the 9th thermocouple section BB which coincides with the location of the fifth thermocouple, and a section CC which coincides with the location of the first thermocouple on the metal rod. Okay, so now we are interested in finding out how much heat is going out, how much heat is passing through this cross section AA. Okay, so how do we know it? Under steady state condition, whatever heat is coming through here, crossing this cross section, I mean, because it's steady state, so there will be no heat accumulation anywhere. So if we consider this portion of the of the rod from T9 to the tip, then there is no accumulation. So whatever heat is entering at this point at T9 at this cross section AA must be dissipated either through the cooling jacket or through this gap. Now this gap between the insulation and the cooling jacket is very small. You can see from the picture here. I mean, it's actually there is no gap, almost no gap. So you neglect that. So whatever heat is heat energy is flowing through this section AA has to be removed by the cooling water jacket. So do you get this point?
Yes, sir. My two-dimensional heat flow.
Two-dimensional কেন বলছো?
স্যার কেবলমাত্র স্যার মানে ওর দিকে তো হচ্ছে না, মানে ইনসুলেশনের দিকে তো হচ্ছে না, সাথে তো আপনার লেন্থ বরাবর হচ্ছে
না এখানে তো within the rod the heat conduction is primarily in the along the length. That is because the length of the rod is much larger than the diameter of the rod.
তো ওটা তো নেগলিজেবল ধরা হয়ে যাবে না স্যার, ওর জন্য ওই দিকের মানে হিট ট্রান্সফার ফ্লোটা আমরা নেব না।
কোন দিকে?
ওই স্যার রেডিয়াল
না রেডিয়াল
স্যার লেন্থ বরাবর হচ্ছে হিট, আর কি
থার্মাল রেজিস্ট্যান্সটা তো রেডিয়াল ডিরেকশনই অনেক কম হওয়ার কথা, কিন্তু আমরা ওখানে there will be heat transfer but there will be a negligible temperature drop. Heat transfer is not negligible. We are considering temperature gradient in the just like what you did in the Fien analysis. You just remember what you did in the Fien analysis. In the Fien analysis also you considered a slender Fien, that is the Fien whose L/D ratio is much greater than 1. Okay, yes. So but there was heat loss from the side. In fact, thermal resistance to the side wall is much less because the distance is much smaller. But because of the small dimension in that direction, you can neglect any temperature variation in the radial direction. Okay, that's why you considered temperature variation only along the axial direction in case of a Fien. You are not neglecting the heat transfer in the radial direction. And if you neglected the heat transfer in the radial direction, then your H would have been 0, which means in your Fien equation m square would have been 0, and it would have become simply a one-dimensional heat conduction in a Cartesian system. Okay, so here also there is heat transfer in the radial direction, but but within the rod we are assuming that there is negligible temperature difference within in the radial direction, but that will not be the case in the insulation because the insulation has a much lower thermal conductivity. So to maintain that the same amount of heat flux which is coming in the radial direction from the Fien, the temperature has to maintain a significantly high temperature difference. Okay.
Yes, sir. Yes, sir.
Okay, so whatever heat is coming passing through the section A, that is going to that is removed by the cooling water. So how much heat is removed by the cooling water? It's of course, if m dot w is the mass flow rate of cooling water and Cw is the specific heat of water, then the rate of heat removal by the cooling water is MW CW times T15 minus T14. That means the temperature rise of water. So it is basically the simple MC delta T MC delta T relation from calorimetry. Okay, so this is the amount of heat that is being removed by the cooling water jacket, and this heat all of this heat must be coming from the fin, crossing the fin at the coming through the rod, crossing the rod at the cross section A. Okay, so this is the amount of heat that is passing through section A. But how do we get the amount of heat passing through section A? By application of Fourier law, which gives minus k at this location times cross-sectional area at this location times dt dx at this location. In our case, it's a cylindrical rod, so cross-sectional area at each locations A, B, B, C, C, they will all be same. But if it was something like a conical rod or rod of any shape other than a cylindrical rod, then this cross-sectional area would have changed. And why is is K going to be different? What is the significance of writing this subscript AA for K? Can you tell me?
স্যার একবার বলবেন?
আমি জাস্ট কে না লিখে আমি কে এ কেন লিখলাম?
Because the thermal conductivity is changing with the change in temperature.
Right. The thermal conductivity will be changing with change in temperature. So, because we are expecting a significant temperature variation from T1 to T9, so thermal conductivity at different temperature locations will be different owing to different temperatures. So to calculate the rate of heat flow at this section AA, I apply the Fourier law where I use all the values corresponding to section A, and I know how much heat is flowing. So that's how so this is one relation from which I can get the value of Ka. How we will do, we will see later. Okay, now if you consider section BB, then the heat that is passing through section BB, this thicker line, the heat that is passing through section BB, a part of it is all of it is not passing through section A, right? Why? Because some of the heat is lost through the side between sections BB and section A. Do you agree?
Yes, sir. Yes, sir. Yes, sir.
I mean, this is the typical fin situation. Okay, so now if we can estimate how much heat is lost from the rod between sections BB and section AA, then we can add that at this amount of heat to this amount of heat to get the rate of heat transfer at section BB. Okay. So for that, I mean, there can be different ways of doing it. I mean, if you are doing it analytically from the fin equation, how would you have done it? You could have done it by simply
energy balance.
এনার্জি ব্যালেন্স কিভাবে করতে পারতাম? ওটা ওই কনভেক্টিভ হিট ট্রান্সফার থেকে মানে H T minus T infinity times perimeter times dx. এইটাকে integrating this, you could have got it.
Yes, sir. Yes, sir. Yes.
But here it is experimentally that is not easy to do. So here we are making a very bold assumption, that is here what we are assuming is that the heat that is entering from the rod into the insulation, it has, suppose this heat which is entering here, it has two paths. It can flow axially along the length of the insulator, or it can flow radially across the insulator and get convected outside. Okay, so of the two, again, because the length of the insulation is much larger than the radius of the insulation. So and here the thermal conductivity is also not high. So if we compare the two, we will find that this will provide a much lower resistance path. That means flow of heat in the radial direction will be much easier compared to flow of heat in the axial direction inside the insulator. So we assume that whatever heat is entering through the entering from the rod to the insulator is passing in the radial direction. That means we have a one-dimensional radial, one-dimensional cylindrical coordinate system for this heat transfer. That is a one-dimensional radial heat flow. So, okay. So do you understand this?
Yes, sir.
Okay. Now, but radial, that is fine. But even in our field analysis, we assume the heat transfer to be just one-dimensional radial at the fin surface when we say that it is only lost by convection to the surroundings. But if the temperature at different these locations, if they differ inside the insulation at these locations, if they differ, then the amount of heat loss, to calculate the amount of heat loss, you have to actually do the measure the temperature at different locations and do a numerical integration, right? But here again we make a very bold assumption. Bold assumption is we justify this assumption in this way, that because heat transfer is very negligible along the length of the insulation. So if there is a negligible heat flow, then there should be a negligible temperature gradient also. So the negligible temperature gradient will ensure that there will be minimal heat flow. That means if there is negligible temperature gradient in the axial direction, then what we can say is the temperature here and at the same radial location here or here, they will not be much different. Okay, so that's why what we are assuming that the temperature field in the entire section between planes, entire region between sections AA and section BB can be represented by the temperatures T12 and T13. That means T12 represents the radial temperature over the entire location from section BB to section AA. Okay, so similarly for
Sir, means one thing I just want to confirm that in this thing, when we are going from A to B, as radially the heat is heat is getting lost. So at point B, there will be means less amount of heat energy than point A. So
why?
No, sir. Opposite. I am telling. Means from
Yes.
B to A, the energy will be less. Now, my question is that, sir, when we are taking it that what you have said, the assumption means then also there will be a little difference in the linear one, because the heat, as the heat energy is getting low in that rod, then insulation means the temperature gradient in the insulation will be also decreasing.
Yes, temperature gradient in which direction? In the radial or axial?
Sir, I am telling in the axial.
Yes, axial direction it will be very less. Axial direction it will be very less. That is why there will be very less heat transfer in the axial direction, because it is providing it a huge resistance. So basically,
Yes,
if you think in terms of thermal resistance, then you have two parallel resistance paths. One along the axial in the axial direction in the insulation, and one in the radial direction. So the radial direction, by virtue of its small radius, by virtue of its much smaller dimension compared to the axial dimension offers a much lower resistance, right? I mean,
Yes.
this inspired, of course, in the radial direction, the only resistance is not the conduction resistance. Also, you have a convective resistance at the surface. And this convective resistance is not because of any flow, but because of natural convection. And here, the temperature difference, it is the insulation is not at a very high temperature, so the temperature difference is low. So the as such, the resistance to convection is pretty high, because the resistance is given by 1 over HA, and H is not high. So
Yes, sir.
so there is a significant temperature difference in the radial direction also. I mean, so there is a significant resistance in the temperature in the radial direction also, but because we are talking of a low thermal conductivity material, so in spite of having a high convective resistance in the radial direction, the overall resistance in the radial direction turns out to be much less than the overall resistance in the axial direction. Okay, so that's
Yes,
why
sir.
heat will be, we can assume that entire heat energy difference between sections BB and sections AA would be due to the heat transfer through through the insulation between the sections AA and BB. Now the question is, so here, I mean, we could have put a few more pairs of thermocouples here. That would have definitely given us a more accurate result, but we have to make a simple setup, not very expensive and not very complicated to run. So that's why here it's more of a demonstrative type rather than getting the exact accuracy. It's not like someone is testing some material and accurately getting the properties. I mean, if that was the case, then we would have to put some more thermocouples. Okay, so here we are. Here we are assuming that the temperature from here to here, there is negligible axial variation in the temperature between sections AA and BB, but there is some radial variation. So negligible axial variation between sections AA and BB, that implies that if you put the thermocouple at any axial position between AA and BB, then the reading of the thermocouple, like this T12 for example, would be representative of the temperature at any axial position between AA and BB, but at the same radial position. Okay, so so now then, if we assume that this entire stretch is at the same temperature, then this becomes a purely one-dimensional radial heat conduction problem. And so we know that if this length is L, if L is the length of the of the insulator, and its inner and outer radii are R0 and Ri, basically not here to here. We are basically interested in the locations at which the thermocouples are placed. So here the location is R0 and Ri. Then we can find out how much heat transfer is taking place between T12 and T13 in terms of the temperature difference between these two locations and these geometric parameters. Okay, so here note one thing, that in the lab sheet that I will be sharing with you, there is a typographical mistake. It should be log RO by Ri, not log RO minus Ri. I mean, it could have been written as log RO minus Ri, but that is just a simple typographical mistake. Please note it. Okay. So at QBB, so that's how you find out how much this branch of the heat loss, how much heat is being lost between sections AA and BB. Add it to the heat passing through section AA, and you get the heat passing through section BB. And again, this heat passing through section BB, you can put it as minus KB minus KA dt dx, everything measured at section BB. Okay. Similarly, if you want to get the heat passing through rate of heat flow through section CC, then also it will differ from section BB because of the radial heat loss between sections CC and section BB. And again, here we assume that this thermocouples T10 and T11, they represent the temperature in this entire region. So we again use a 1D radial heat flow expression, and we get the heat law amount of heat transfer between sections BB and CC added to QBB to get QCC. So that's how we get the heat transfer at the rate of heat flow through each of these sections, and for each of them we can use the Fourier law and write it as minus KA dt dx. Okay, so next what we do, so this is the procedure. So now we have to see, so then what it happens. So if we can find out how much heat is carried away by the cooling water and how much heat is lost through between sections ABB and BBCC, then we can find out the rate of heat flow through the three sections. And then at each of these sections we know the cross-sectional area because the geometry is known. If we can measure the temperature gradient at these three sections, then we can measure the thermal conductivity also at these three sections, and that gives us the thermal conductivity of the same material. So why they should be different? They would be different because they are at three different temperatures. Okay. Okay. So up to this part, is it clear?
Yes, sir.
Okay. So now let us go to the procedure. So as usual, put on the electric supply, start the cooling water supply through the jacket and adjust it to about 300 to 350 cc per minute. Okay, so that why this particular value? So that you get a reasonable amount of temperature difference, not too high, not too low. Okay, so how will you do it? You will just collect the water in some graduated vessel, graduated cylinder or something like that, and note for a specified amount of time, and note how much water has been collected in that graduated vessel. So so from that you know how much what is the rate of water flow. Of course, here we are assuming that over that interval the water flow rate is not changing. It's not like there is a huge fluctuation of water flow rate. Basically, it is connected to a tap water supply. So normally, if you're not adjusting the tap in between, there should not be any big fluctuations. Okay. So then you apply the input power by operating the thermostat, say at 50 watt or some such voltage, and wait till the steady state is reached, and then note down the temperature readings 1 to 50. So how will you know the steady state has been reached? You have to keep on noting the temperatures at regular intervals, and when you see that the temperatures are not changing over a significant period of time, then you know that the steady state has been reached. Then you take down the readings, temperature readings 1 to 15. Also note the mass flow rate of cooling water. Actually we will not be able to note the mass flow rate of cooling water. You will be able to note the amount of water that has flowed in a given period of time. So you have to note the the time elapsed, and you have to note the amount of water collected. From that you will get the mass flow rate. So that completes the experiment. So after the experiment, so here there is only one set of reading. After the experiment is over, again you have to put the dimmer state first to 0 position and then put off the main switch. Actually, you should put off even after putting off the main switch. After some time you should stop the cooling water. You should stop the cooling water supply so that it allows the rod to cool
The
down.
heater too means cool down, yes.
হিটারটা কুল ডাউন করবে না, মানে রডটা কুল ডাউন করবে,
That's about
হিটারটা তো
heating rod basically.
হিটিং রডটা, হ্যাঁ। ওকে, so these are the observations: voltmeter reading, ammeter reading, and room temperature. The voltmeter reading and ammeter reading you will not be using here, unlike the other experiments, unless you want to do some kind of energy balance. Then the amount of water, cooling water circulated, Cc, and the time of cooling water flows. That means the time over which you have collected the water flow, the water flow. So that time is here, and the amount of water that is collected, that is here. And the outer radius of insulation and inner radius of insulation, you are writing it, but actually it is given in, you are not actually measuring it. It's already given in your sheet. I mean, from the given data you have to put it down, and then you have to measure the temperature at the 15 thermocouple locations. So that completes your experiment. Then what should be your calculation? The mass flow rate of water, that should be equals to volume of water collected. Mass of water collected is volume of water collected times density. Then the mass flow rate of water would be this mass of water collected divided by the time interval. So that gives you the rate of flow of water. Then heat flow rate through section A, that would be this m dot w times cw times delta tw. That means how much temperature rise is taking place multiplied by the thermal mass flow rate of water times the specific heat. So that gives you the heat flow rate through section AA. Similarly, you can get here you calculate by knowing the temperatures T1, T12, and T13, knowing the distance between sections AA and section BB, and the radial positions at which T12 and T13 are mounted. You get the rate of radial heat loss between sections AA and section BB. Okay. So once you get that radial heat loss, so you add it to Q dot AA to get heat flow rate through section BB, which is Q dot BB. Similarly, by calculating the rate of radial heat loss between BB and CC and adding it to Q dot BB, you get Q dot CC. So now you have got the actual rate of heat flow through the three cross sections. Okay. So cross section of the metal rod. Okay, so here I have a typographical error. Let me correct it. So this should not be pi ri square. This should be pi by 4 d square. Okay, because ri is the location of the ri is the where is the equation? So this should be pi d square by 4. Where is the older version? Okay, so I'll just note the correction. This should be pi d square by 4. Okay, the cross sectional area of the metal rod. So then temperature gradient at A, that should be slope of temperature distribution at location A. So how you get that? You plot the the temperature at the 9 locations and do a best fit curve, draw a best fit curve through it, and whatever you get the slope at any location, that will be at that particular location at A, that would be dt dx at A. So this is how you get thermal conductivity at location A, which is temperature T9. Similarly, you get the thermal conductivity at location BB and location CC. So you get 3 thermal conductivities at 3 different temperatures, and you plot the thermal conductivity as a function of the temperature. Okay. So in the results, you have to complete the tables, show all the steps for one run as sample calculations, and plot T1 to T9 as function of x for x, and then from there from the graph you can find out graphically, or by doing a curve fit you can find out what should be the temperature gradient at the 3 locations, and then plot k as a function of Ti. So this will be the experiment. So now let me just show you the actual diagram of the So this is how it looks like in a schematic way, in a sectional view. This is the heater, this is the insulation, these are the 9 thermocouples on the metal rod, 4 thermocouples in the insulation, and the 2 thermocouples at inlet and exit of the of the cooling water jacket. Okay, so here it is entering and here it is leaving. A more detailed view of the positioning of the thermocouples, you can see that all the so this length was given, if you remember, this is 176 millimeters, and all the 9 thermocouples are placed at equal intervals, so each interval is 22 millimeters, so that makes it 176 millimeter, and the axial distance between the 2 sets of radial thermocouples, that is T10, T11 and T12, T13, that is 100 millimeters. Okay, so where exactly it is not mentioned, but it is somewhere in between BB and CC. It is about 100 millimeters. The distance is about 100 millimeters. And similarly, and this T10 and T12, they are placed at a radial location of 40 millimeters from the axis of the rod, and T11 and T13, they are placed at at a radial distance of 60 millimeters from the axis of the rod. Okay, so these are the measurements that you have to do. This is, and I have just told you what you have to do in the report. So this completes our our discussion on the experiment. So here also I have, just to show how the experiment runs, I have prepared prepared this digital version, but problem is that unlike the previous 2 experiments, here many of the details are not available in the drawing, so we have to make certain approximation. So the results are not in very good agreement with what we have in the experiment. Also, the experimental results also at certain places that they look suspect. I mean, because it is some old result that I had to take, so there could be some error there also. So don't be too much concerned about the exact values, but this is how we are getting. Okay, so basically these are the input things that you have to give: the ambient temperature, the water inlet temperature, the volume of water collected, the time of collection, and the thermostat input. Okay, so there you have to do some calculations. So let us see. So ambient temperature, let us put it as 25. Water inlet temperature, so let us put it as 27. So the volume of water collected, let that come out. So T14 has already come out as 27. I mean, this is one of the readings actually. Then volume of water collected, let it be 500 cc, and time of collection is, say here you get say something like 30 seconds. Okay. And now you have to give the thermostat input. So let us put it as 90. So you get, the moment you put the thermostat input, you get the voltage and the current as you would actually get in the experiment, and these are the 15 temperature values. Okay, so these are the values that you have to take, and then you have to do the calculations. I have not given the calculations as usual, so you can just check it like this. I mean, this is a very crude set. This is a very crude set. I mean, this needs to be improved. For example, so here also, what we have done. Well,
Sir, as we are going from T1 to T15, means the temperature will be decreasing gradually, though.
Not from T1 to T9, it will be gradually decreasing.
Yes, sir.
And T10, T11, from T10 to T11 there will be a decrease. From T12 to T13 there will be a decrease. Again from T10 to T12 there will be a decrease, because T10 is somewhere in the middle. It is much upstream of T9. So there is no direct connection between T9 and T10. In fact, T10 should be higher than T9. Similarly, T12 should also be higher than T9. And T14 and T15 are two entirely different things. Okay. So actually here also there is a nonlinear equation. I mean, we have to find out how much. So there are in this, when I prepared this model, when I made this model, actually this is a very interesting, comes out to be a very interesting heat transfer problem. So what I did when I prepared this, when I was making this model, so I do not know what will be the values of heat transfer coefficient H from the side of the fin, and what will be the heat transfer coefficient from the tip. So from the tip, what I did, I just followed that the QA that I took as HT times T9 minus T infinity. So if I get some estimation about the heat transfer, about the heat loss from the tip, then I can find out the heat transfer coefficient. So for that, there is again a nonlinear equation that has to be solved, but this function is given here, that the tip heat transfer function. So to get it going, you have to use this Golsik function as before. You have to set it to 0 using the value of the unknown. Here the only unknown is the heat transfer coefficient. So changing it, you have to do it. So you get this get this value. Okay. So for that, what I have done, I had to assume the convective heat transfer coefficient between the coolant water and the part of the rod immersed in the coolant water. So that can be done with more sophisticated correlations, but I just assumed some value here, some reasonably high value, 100. Similarly, and what I did for the radial heat loss, the radial heat loss, the fin, there are two resistances, as I said, the conduction resistance through the insulation and the convective resistance at the outer face of the insulation. So using these two series resistances, I derived an equivalent resistance in terms of some effective thermal conductivity. Okay. So do you understand this? I mean, instead of these two resistances, I put an effective convective heat transfer resistance. So basically it would become 1 by HF times the curved surface area of the curved surface area of the of the rod. That should be equal to the 1 by HA at the insulation at the outer surface of the insulation plus the thermal resistance to conduction through it. So that way I calculated an effective H, and so that I could do a fin analysis. Okay. So this is how I did it. So this is, I'm still not very happy with this digital thing, but still it gives you an idea. I mean, the working wise, it is exactly how the experiment goes, but the actual values, they need to be improved upon. I mean, they can be improved upon. Moreover, what I did, I tried to do whatever can be done in a spreadsheet, so that it can be easily done, and we don't need to have any special software. Okay. So basically that completes our discussion. So British, you can stop the recording. So I'm stopping the presentation. Okay. Pritesh, what you